first part of the presentation. So you might have seen this in other presentations from Quantinuum so far at this conference, but we have an integrated approach to quantum computing, really after the merger with Cambridge Quantum a year ago. By integrated approach, I mean that we have our offerings, such as a good example is our quantum chemistry offering called Quanto. It's built on Ticket, which is an open source toolkit. The advantage of Ticket is that it makes it easy for users to use Quanto, but use it with any backend platform that almost any platform that they wanted to experiment with. So if you've collaborated with us on Ticket, chances are then your platform is included in our Ticket toolkit. But you might remember when we did have Honeywell Quantum Solutions, we did have our own hardware. We brought that to the merger called the H-series hardware, and I'm going to be talking about that today. So in terms of hardware, we've had a very strong year of development. So this slide is world firsts that have happened in our facilities, our labs on the hardware side. A couple of the demonstrations, are first-time measurements of quantum volume, and I'll talk about that a little bit more. But we started the year with a measurement of quantum volume of 2048, and a couple months ago, maybe 2 months ago, we had a quantum volume of 8192. So we continue to advance the quantum volume of our machines. We also have spent a lot of focus on quantum error correction. When we were here last year, we reported on the first real-time corrected qubit. And about mid-year, we did a simple logical circuit that outperformed a physical circuit. Those are on our commercial tests, our commercial products, H1. We also have test beds, and these test beds are meant to prove out maybe a very specific capability or very specific functionality. One of those test beds was used to demonstrate a world record SPAM, or state preparation and measurement, in a barium isotope. And another one was used to transport a barium-ytterbium chain around a junction, or basically around a corner of our trap, and you'll see what that means in a couple slides. This is the roadmap that we've showed before, laying out our trajectory over this decade. And those first time ever demonstrations on the prior slide really set this roadmap up for success and show that we're well on our way. So right now we have system model H1, which is a linear trap. And I've got a little bit more of that on the following slides. This is available through Azure Quantum, and Fabrice will be talking about what people and Azure customers are doing with that today. System model H2 is soon to come, and it takes that linear trap of H1 and now puts 2 copies of it side by side, connects those 2 copies in this racetrack formation. And then system model 3 starts to change and look a bit different. It's now moving into a grid structure. So if you've ever been in downtown Manhattan and been on the streets and avenues, that's what you can expect from H3. And that demonstration of showing how we could turn the corner is now become really important, because all of these little corners we call junctions. And to get qubits, 2 species of qubits to go around those corners at high speed with acceptable heating has been longly eluded in the field, but something we were able to demonstrate this year. That really forms the basis then for the continued scaling of our systems. So to back up now and talk a little bit more about H1, if you haven't already guessed, our qubit states are states inside of a trapped ion, so an ionized atom. And our architecture, though, is unique. It is the quantum charged coupled device, or QCDC Architecture. This was invented by pioneers at NIST several decades ago, but this is how we've adopted it for our commercial systems. Here's a picture of the trap, and we can confine our ions above this rail-like structure. We can do some pretty interesting things with these ions when they're confined to this rail-like structure. You can kind of see in this animation. First of all, we can move the ions along this rail structure, and we can also reorder the ions. So you saw that we made one jump over the top of the other one. So we have that specific control over it, that we can do those maneuvers. And this means that the qubits move around, our topology is not fixed, so you now have a lot of flexibility in the different types of things you can look at. When we move the qubits, we're usually moving them to these dedicated gating zones. So these are these blue zones that you see here. And you might have seen during the picture that once you got to these gate zones, then a set of lasers came and performed the 2-qubit gate. So these are isolated regions. They're done purposely in these isolated regions, and that's to make the lowest noise possible. And you can see we have 5 of those, so we can do 5 parallel gate operations at once. As we have larger systems, they will have more gate zones. In this animation, it's showing the ability to do an arbitrary pairing. Oh, I lost my gate there. So this is showing how to do arbitrary pairing. So we've taken 2 arbitrary qubits, put them together, and then with our other maneuvers, we could take 2 other arbitrary qubits and put them together. This makes all-to-all connectivity. And Fabrice will be talking a little bit more about this, but this is a major advantage, especially at these early stages with NISQ hardware. And then the last thing we can do is we can isolate the atom, or the ion, and make a mid-circuit measurement. So we can pull it off to the side and measure it. Mid-circuit measurement is an important tool, but it's very important that it has low crosstalk. So by isolating it, we can make it sure that the measurement itself doesn't pollute the other ions in the circuit. The mid-circuit measurement then allows conditional logic to happen in the circuit, and then we also have the capability to reset and reuse the qubit for later in the calculation. So to talk a little bit more about these differentiating capabilities, all-to-all connectivity, as I mentioned, is very important. If you have a fixed topology and you're trying to entangle 2 qubits spaced far apart, you have to do a lot of intermediary gates. Each of those gates could have some noise associated with it or will have noise associated with it in these early stages. So this whole operation can have an aggregate, a lot of noise. In our system, we can just physically move this qubit and this qubit together, do the entanglement in one step. That, and we also have these high fidelity gates. So we can get the high fidelity gates because we can isolate the pair of ions, do the operation in a very quiet and controlled environment. This is from our data sheet on our commercial system. Our 2-qubit gate fidelities are limiting error, and it's at 99.7%. We continue to work on this and bring this down with some of our test beds. And then the last feature that I wanted to mention that we've added relatively recently is arbitrary angled 2-qubit gate. I've left the math here for the experts if they want to look at it, but I think the circuit diagram is a little bit more intuitive. To do an arbitrary angle entanglement, most systems require that you have 2-qubit gates sandwiched between a single qubit rotation. We can directly do that with a gate, so that saves you a 2-qubit gate, which again is our limiting noise. And also the noise on this 2-qubit gate scales has the angle. So for small entanglements, that has lower noise than our fully entangled 2-qubit gate. The way we measure our progress and make sure that we're advancing not only the number of qubit, but also the performance of the qubit is that we look at quantum volume. When we launched our system in 2020, we set the goal for ourselves to increase the quantum volume 10x per year for 5 years, so that's this gold line. And then the data points show how we've progressed with different systems available. And so again, our last measurement was made in October of 8,192. This is 2 to the 13. This is made on a system that has 20 qubits. And this system is commercially available, as well as this system, which is our H1-2. It only has, at this time, it only had 12 qubits. So the maximum quantum volume it could have was 4,096. So before I turn it over to Fabrice, I'll just summarize by saying our approach is, I think, unique in that we start with quantum. We think that's a very important feature of a quantum computer is we start with something quantum. It saves a lot of fabrication issues to start with quantum, but then the effort is to keep it quantum and reduce the noise as much as possible. And our focus is not on adding qubits. Our focus is on doing more with every qubit. Every qubit counts. So as important as it is to continue to build in more qubits, it's equally important to make sure that the fidelity of those qubits enable us to do meaningful things with those. We provide a unique toolbox for users. I've mentioned them, the high fidelity gates, mid-circuit measurement, all-to-all connectivity, so on. This provides a lot of flexibility to try out new algorithms, but to also try out the things in quantum error correction, which we know are coming. As far as our business model, we do have a unique business model where we continually upgrade our systems. So if you come to our labs and see our systems, you'll notice that they're large systems. That's because we go in and change the lasers, change different pieces inside to continually upgrade it, but our customers then get access to the latest and greatest capabilities. We provide emulator. We really focus on quality, meaning when you use our machine, every time you should get the same results. It's highly repeatable. And then we provide a lot of specialized support for people to take advantage of these toolkits. So with that, I'll turn it over to Fabrice for the rest of the story.
Thank you very much, Jenny. Clicker, perfect. My name is Fabrice Frachon again. I'm the program manager lead of the Azure Quantum service. I also oversee the technical partnerships with our hardware providers and our solution partners. The partnership that we have been having with Quantinuum, I must say, has been one of the most rewarding. In particular, in the past 2 years, we've been working very closely on the topics of hybrid quantum computing and what can be done in this field. Hybrid is something that you've heard a lot, but when you look at what is being done today in the world of hybrid is that most of the classical compute that happens is happening on the client side. And what we've been focusing on in particular, and that I want to discuss today, is what are the things that we can do to move some of the classical compute into the quantum machine and unleash a new generation of quantum algorithms. So before I get into that, I want to talk a little bit about Azure Quantum. Really at the center of what we're doing in Azure Quantum is really to enable you to learn and experiment with a wide variety of hardware system, of type of qubits. And in addition to that, in parallel to that, we really want to support you on your journey to fault-tolerant quantum computing. And there are two things in particular that I want to illustrate on how we support you on that. 3 weeks ago, we released a new capability that we call the Azure Quantum Resource Estimator. And this tool allows you to take your algorithm and estimate the number of physical qubits and the computation time that will be necessary on a fault-tolerant quantum computer. So this is a first in the industry, and really that's going to support you on your journey to fault tolerance. The second element that we've been working for many years now is a language, Q#, that enables you to richly express capabilities that are mixing classical compute and quantum compute. And we're going to see all the power that a language like that can enable today. The last thing that I will point out is that this journey that we're in together on quantum computing is obviously complex, long, and it's also an expensive journey. And we want to make sure that we're here for you, support you through grants, and so when you have research, come to us, we will be supporting you, and I'll talk a little bit more about that. So 1 year ago, actually, at Q2B, with the members of the Quantum Intermediate Representation Alliance, we performed 3 what I will call foundational demos for hybrid quantum computing. The first 2 demonstrations really showed that you're able to indeed perform classical compute and quantum compute together in the quantum machine. The third one was a way for you to say, well, you're going to focus on developing the algorithms, and the compiler tool chain and the hardware backend is going to focus on what they know the best, how to optimize your algorithm for their specific systems. So in the past year as well, what we've been doing is develop a very rigorous taxonomy of hybrid quantum computing, because we hear so much and it can mean so many things. Today, we're really in the world where the computation is happening on the client. And so the way to think about these different levels of hybrid is that each level is bringing a level of maturity with a tighter and richer integration between the classical compute and the quantum compute. And what we're bringing today with the integrated quantum computing is indeed this integration of these 2 elements that are core. So this is a very quick representation of integrated quantum computing from an architecture point of view. You see the classical loop here that is at the center, that historically has been run at the client, then moved to the cloud for a variational algorithm, and that now we're able to move some of these elements inside the quantum machine. So what does that mean exactly to have integrated quantum computing available? It means, and I'm going to ask you to focus inside this blue box of everything that happens, but inside this blue box, you're able, and that's all running on the hardware provider in Quantinuum in that case, you're able to perform arbitrary control flow. So you're able to take a measurement and decide what to do once you did this measurement, and you're able to perform classical computation in the backend again, all the while the physical qubits are alive. So I'm going to repeat. You're able to do arbitrary control flow, you're able to do classical computation while the physical qubits are alive. So this is really going to unleash this new generation of algorithms. And really the net benefit is you can dream of having exponential reduction in number of shots when you run this type of experiment. And all of that is really powered by the work that the QIR Alliance has been doing in these past 2 years with all its partners. So let's take quickly a case study. So we've been working with the Louisiana State University and the University of Oxford to take one of the algorithm, the quantum neuron bound machine, that they wanted to adapt using these hybrid capabilities. So the quantum neuron bound machine is a quantum version of a neural network. And one of its particularities is that it's using repeat until success circuits. And the number of these circuits is more or less dependent on the total number of neurons. And this is a fine algorithm. The main challenge of running this algorithm is the number of repeats that you need to do, and the level of noise, and this number of shots that you have to do in practice make it just unpractical to run because of the time and the cost that it will take. So let's look quickly about the challenges that this team was facing in implementing initially this algorithm. The first one is that in many traditional architectures from hardware vendors today, you have a low qubit connectivity. And what it means when you have low qubit connectivity is that you need to perform swapping operations. When you perform swapping operations, you have errors introduced that are propagating and so on. And so it makes the level of noise unsustainable. The second element is that you need to run all your circuits. And once you have run all your circuits, you can perform the post-selection on the client. Again, this means lots of shots, this is slow, this is extremely expensive. And so what has been enabled with the H series and with this hybrid architecture is that the all-to-all connectivity of the H series and the low error rate that they provide is resolving the first problem they had. And when, in addition to that, you take the arbitrary control flow, the mid-circuit measurement, the qubit reuse, the loop, and the classical function calls that you can do while the physical qubits are alive, you're able to exponentially reduce the number of shots necessary. So I'm not going to share today the results of these experiments because I want to leave the researchers to share these very exciting results. But we have multiple projects right now that are running, and I'm looking really forward in the next few weeks to share these results with these researchers. And I'll close very quickly by reminding you we have very generous grants that we provide to all the researchers up to $10,000 for your projects. Please do not hesitate to reach out to us. This is our way to contribute to the ecosystem. And if you want to get notified of new features availability, follow this link as well. Thank you very much, and I can't wait to work with you on these new projects.